Hello students, in this video we'll discuss elementary matrices. The elementary matrices come from the elementary row operations. Okay, and so what we're going to do is let's look at some examples and then we'll figure out how to generalize these examples. So here's an example. Our first example of an elementary row operation is changing rows. Changing rows. Okay? So if I want to change two rows, I'm going to do, let's look at this matrix over here, 0, 0, 0, 1. I keep the first row the same, right? And then I do a 0, 0, 0, 1. That looks like I'm taking the fourth row of the identity and putting it in the second row. Then a 0, 0, 3. Looks like 3 stays the same. 0. And then how about a 0, 1, 0, 0, okay? What would this do to a matrix over here? If I plugged in A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, and D1, D2, D3, D4. Let's see what would happen. Again, first row dot column, the first row is not going to change. This identity part of the first row means the first row is preserved, A3, A4. And then now what's going to happen is as I do the second row dot columns, I'm going to get the D row, D1, D2, D3, D4. The third row looks like it's going to stay the same, C1, C2, C3, and C4. And then I'm going to put the second row in the fourth row. So I have a B1, B2, B3, B4. So it looks like this matrix has done what? This matrix over here has interchanged rows 2 and 4. Interchanged row 2 went to row 4. So I've changed rows. That's an example of changing rows. Now notice over here that if I change rows 2 and 4, if I want to undo this procedure, if I want to find the inverse of this matrix over here, the inverse of this matrix is itself. Because if I change rows 2 and 4, and then change rows 2 and 4 again, I'll get back to my original configuration. So note over here, the important thing to know is that this matrix over here is 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and then 0, 1, 0, 0. Inverse is just itself, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and then 0, 1, 0, 0. So in other words, the inverse of this changing row matrix is still a changing row matrix, it's the same thing. So the inverse stays in the same class, which is very important for us. And that's one example. Another elementary row operation, so we can change rows, we can also scale rows, right? So if I want to scale rows, okay, so let's do a simple example of this. If I had a 1, 0, 0, a 0, 4, 0, and a 0, 0, 1, and I wanted to hit that with my matrix A1, A2, A3, B1, B2, B3, C1, C2, C3, we can quickly see that the first row is not going to change, A1, A2, A3, nothing's changed there. But now what's going to happen? All of the entries of the second row are going to be multiplied by 4. And then the third row stays the same. So the effect that this matrix had over here is this was the identity matrix, except now what's happened is I've taken the second row of the identity matrix and multiplied by 4, which is corresponding to scaling the second row by 4. So this multiplies the second row by 4. Now, I can undo this procedure by noting that if I did this matrix over here, 1/4, 0, 0, 0, 1, and then 1, 0, 0, 0, 4, 0, 0, 0, 1, will just give me the three-dimensional identity matrix. So in other words, if I scale a row by 1/4, I can undo that procedure by scaling that row by, if I scale a row by 4, I can undo that procedure by scaling by 1/4, right? So in other words, the inverse of this matrix over here from this class of scale row is of the same class, right? So now I would say if I do the inverse of the change row class, I remain in the change row class. If I do the inverse of something in the scale row class, I remain in the scale row class. So it's preserved under inverses. And what's the final row operation we have? The final row operation we typically think about is the idea of multiplying one row, adding one row to a multiple of another row, okay? So the final example is doing something like what? So let me do this, I'll give an example. if I did 1, 3, 0, and then 0, 1, 0, and then 0, 0, 1, applied to our matrix A1, A2, A3, B1, B2, B3, C1, C2, C3, what would happen over here? Well, notice that the second row and the third row would stay the same, but what this would correspond to is this would correspond to a A1 plus 3B1, plus, then the next entry would be what? Next entry would be A2 plus 3B2, and then A3 plus 3B3. And then the B1, B2, B3, C1, C2, C3, right? So the effect that this thing had is I've added 3 times the second row to the first row. So this would correspond to 3 times row 2 plus row 1, replacing row 1. Now, of course, if I wanted to undo this, it's easy to check that this thing over here, if this is my matrix over here, the inverse of this matrix will be 1, negative 3, 0, 0, 1, 0, 0, 0, 1, like so. So the inverse of the matrix of this form is also of the same form. So how do we write down these things in general? So in general, we have 3 types of elementary matrices. We have our scaling type. Okay, so our scaling type is going to be a matrix of the following form. It's going to be E1 hat, where there's a standard basis, all the way up to lambda E I hat. So in other words, I've changed the ith row by a factor of lambda. Now these are columns, of course, En hat. This is lambda scale the ith row. And these, of course, are columns, right? So that's a column, 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 right? So the columns, I'm doing all of these elementary matrices on the what? I'm doing these elementary matrices on the left of the matrix itself, right? So note, multiplication always occurs on the left. For rows, okay? Excellent. But the corresponding matrices are column-based, okay? That's our scaling law. Then we have our what? Then we have our swap, our exchange, we'd have E1 hat, E hat J, E hat I, E hat N. Well, what have I done over here? So this would be correspond to the what? That would be the ith column over here, ith column, and this would be the jth column. Okay? And this is interchange. Row I turns into row J. And the last thing we do is we do this adding, right? This combination. So we have a combination one. Okay? And so the combination one is the following, is E1 hat, and then I can have a EI hat plus lambda times another row, EJ hat, EN hat, right? And this corresponds to replacing row I with row I plus lambda row J. And of course, what are the inverse of these things? So the inverse, if I do the inverse operations, the inverse of these operations, the inverse of a lambda scale would be a what? Would be a 1 over lambda scale. These would be the inverses, 1 over lambda scale. The inverse of exchange is itself. It's self-inverse. And the inverse of combinations is the negative. So if I have a positive lambda over here, I would have a negative lambda for the inverse. So we see that the scaling matrices, the exchange matrices, and the combination matrices, the inverse of those matrices are of the same exact form. Now, of course, it might be corresponding to the multiplicative inverse or the additive inverse, but they're going to maintain the same structural shape. So it's very easy to find inverses of these elementary matrices. And now the point is that for any, the idea now is that if I can find a sequence, E1, E2 of these elementary matrices, that when I hit them with A, I maybe say that A was like an n by n matrix, and I got to the identity matrix, then that would say that all of these elementary matrices multiplied together would be A inverse. That would be A inverse. And what we've done over here is that you might say, well, why would I want to write A inverse as the product of these matrices? Well, all of these matrices, E1 through E2, En, are these elementary types. And so what I've done is I've constructed a factorization algorithm for finding an inverse of a matrix in terms of matrices that are very simple to invert themselves. So I've basically factored A inverse, or for that matter, factored A by taking the inverse of both sides of the equation, so into very, very elementary pieces. And that's going to be one of our first examples of matrix factorization into, maybe there's a lot of these matrices, but they're all very easy to interpret. So I have a whole bunch of easy to interpret matrices, which basically altogether comprise the matrix A or A inverse. Thank you very much.